Good morning. We start our lecture on fundamentals of material science. Please let me know if you have problem hearing me by sending me a message. Otherwise, we carry on. We have stated that materials are any sort of structure, even of very small dimensions, which is able to withstand a force. In making a larger structure, here I do the example with the bicycle frame, because it's a simple object which was very successful, which is very successful because we have manufactured bicycles for over a century, well over a century, and this still works as a structure. You may be sure of the fact that bicycle frames are supposed to withstand a number of different forces, because you use the pedals to move around, and therefore they coupled with the pedaling. There is the weight of the cyclist in the first place, and there is a kind of impact, which is a dynamic force, which is obtained by the fact that the road is not even, and then you can push with your weight more or less, depending on the slope of the road as well, and of course of your speed. Impact is different from indentation. You may remember that we were measuring indentation to assess the hardness of our materials, and indentation means that you push with a tape or with a ball, a hard ball, on your surface, on your material surface, and then you measure the dent you get. Impact is dynamic in the sense that you drop something, which might be also your body, when you push with your body on the structure, and then you remove it, and then you push it again, with it again. This is very important impact in terms of engineering performance, of assessing engineering performance. We'll discuss it also later on, because it's very important when we come talking about composite materials like glass fibers or carbon fibers. Glass fibers own the majority of the market in terms of composites, by the way, whilst carbon fibers are more performing, they perform better, and they constitute a niche which is important in terms of performance of what we want to achieve from that. In fact, you may see that, for example, coming back to our example, mountain bikes for running, for having races at a competition level, are usually made of carbon fiber composites. Whilst in other cases we use other materials. We are interested, of course, in material science a lot to damage. Here you're shown with some examples of damage in carbon fiber composites, and also in aluminum bicycle frame, damage close to welding. Of course, the materials are damaged in a characteristic and different way, depending on the real structure of the material, the very structure of the material, and of the type of force which is applied. So there is always a question of material selection. Material selection is central to material science. So a definite structure can be obtained, can be made using different materials. Of course, with different characteristics. You can use stainless steel, for example. Stainless steel means a steel which doesn't suffer an early damage during especially to corrosion. And you may have stainless steel with a ferritic structure, therefore with alpha iron, with an austenitic structure, therefore with gamma iron, and with a martensitic, therefore which was subjected to some heat treatment of hardening and tempering, and then you get to this tetragonal structure. We discussed this already last time. Then you can have an aluminum structure. It's quite obvious that this is lighter than a steel structure. Even if you don't know anything about the two metals, you may easily see that aluminum is lighter. Titanium is in between in terms of weight, of density, between aluminum and steel, but it constitutes a niche because, well, it's very resistant, and also it doesn't got rusty. You don't get to have corrosion because, like aluminum, you have a passivation effect. So passivation means that an oxide is formed which is pretty adherent to the surface, and so in practice the surface is not exposed to be corroded. Then you have carbon fibers. Here the weight is lower, but you may find problems on the fact that you have two different materials. You have fibers and the resin, which is normally epoxy resin, and you have the problem of bonding between the fiber and the resin. Also, you have the problem that carbon fibers have a considerable tensile strength, but they are brittle, so they break suddenly. Bottom right, you see another particular application. Well, of course, this is quite a niche in a sense, and especially produced in some countries which have bamboo. Bamboo is diffusing a lot. It is part of a large productive system. It wasn't supposed to be a structural material, so a material which was able to hold in a complex structure with considerable weight. But it's this is changing. This is changing because we are able to use this, which is one of the natural fibers. I define natural fibers, fibers which are not obtained from synthetic materials like carbon fibers, which are obtained from graphite, but with a synthetic process, and even glass fibers or Kevlar fibers are the three most important fibers for composites. Then there is also basalt fiber, which recently has come into interest, but not for bicycle frames. You have these natural fibers, and I would like to dedicate a little bit of time later on in the course. They are more sustainable because they are part of the productive system that produces other products, for example, food products, for example, textile products, and therefore you may find out that you are able to reduce considerably the cost because you planted bamboo, you have already bamboo stems, so why not using them to create a structure? This is a possibility, this is an option, which of course compares not to on the same level with say a carbon fiber frame, but on the other side you may have something which is more sustainable, which can be easily repairable, because in the end you may replace one of these tubes which are constituted by bamboo stems quite easily. and the cost might be reduced in some situations in some countries. Also because this might be the waste, these bamboo stems might be the waste of another system. For example, with bamboo fibers, I make textiles like bamboo viscose, and therefore I have this kind of waste of textile industry, and I can make another structure. The use of waste is becoming very important in engineering in terms of sustainability. And this is something which can create a lot of discussion, of course. Therefore, I don't go into details about that because we try to concentrate in knowing better materials, their relations, and please remember, research teams. This course is about research teams. There is a huge number of research teams into material science, and it's important that you get curious, that you get interested into some of these to try to understand what's going on and what can be the perspective in the next few years and in the next decades. So, of course, let's compare these 5 bicycle frames which were in the previous slide. We have different densities, therefore different weights. Of course, the weight of the structure, well, this is not complete in the end. I will complete it later on. The weight of the structure depends on the frame tubes, on the diameter of the tubes. And this is quite obvious, but this hides another concept which is much more interesting, much more crucial, is that if we change material, we need to change also the design of our, in this case, our bicycle frame. Therefore, we need to change the diameter, the thickness of the tube in the first place. And we might also change the relative position of the different tubes between them. Because, for example, welding, when you involve metals, you normally weld the different tubes with each other. Welding is performed better at some angles than at some other angles. And with some thickness, some thickness are required. You may need to make your bicycle heavier than needed by the simple weight of the cyclist or the other force, just because you need to weld in a suitable way. Okay, we were talking last time about corrosion. Corrosion is a big problem. It's a big problem in metals, and it's a problem that leads in a number of cases, in the majority of cases, I would say, to the final failure of metal structure. Corrosion, or the application of a force which exceeds the strength, the allowed strength, or you may have failure due to fatigue. When I say fatigue, I mean cyclic loading. Fatigue means cyclic loading. Cyclic loading may also mean that, for example, you, coming back to the example of the bicycle, you pedal for a number of times, for a number of months or years, and then you can break your chain, for example, your bicycle chain, because you have subjected your chain to rotate, to make a complete cycle for hundreds, thousands of times, millions of times in some cases. And that's why you, in the end, you have failure, which is an abrupt one, even if you didn't exceed the maximum strength of your chain. So you didn't pull to the ultimate strength, to its ultimate strength, but you solicited, you loaded it for a large number of times, which we call cycles. Every time that chain rotates, it's a cycle. Of course, fatigue is a very difficult problem in engineering, and we need, there is also fatigue corrosion. The metal can get also corroded because it has been used a large number of times, and so it was subjected to a stress which was high, or it was subjected to fatigue, and the two things combined. Last time we have seen also some corrosion which have been not correlated directly with mechanical performance, with mechanical loading, but which have been correlated, for example, to some chemical action. You may have an acid which interacts with your metal, and therefore, so a very low pH, and therefore you have a direct chemical attack, which might happen. For example, if you have hydrochloric acid, it might interact with metal and producing some nasty pitting. Pitting means that you have holes, you create real physical holes, which might be very deep, which might go very deep into the thickness of your metal, because this is a direct attack. Then you can have a kind of anodic zone, a small anodic zone, which again produces some pits, but not for the fact that there is physically an acid in that region, but because there is an anodic zone which is quite of limited dimension. When I say anodic, the anode is the electrode where oxidation takes place. Please don't get offended by the fact that I am remembering to you all these things. I think these are basic. But it is important that we are clear about these terms. So it might happen that oxidation occurs in a very small area, concentrated area, and then you have pits, like in direct chemical attack. Or you can have some anodic zones, which is intercalated between some other cathodic zones. For example, which goes into interstices, so which penetrates, for example, in areas which are not very easily accessible. In many structures, you may find out that there are some areas, let's come back to bicycle frame. For example, there are some areas in your bicycle frame which are not easy to be cleaned. These areas can be subject to the formation of crevices, or so of corrosion into interstices. Because they get dirty, they might be subjected to the attack of chemicals, and therefore they might be damaged with the formation of not pits, but crevices which are more extended in length. Pits are really points. Then you can have other types of corrosion, like the film form or lamellar corrosion, which is typical of the tin cans. That's the most normal case. Tin was made into alloys with iron, usually to contain food, to contain canned food. So therefore, in the food industry, this is a long. This has a long history, over a century of tin can. For over a century, tin cans have been produced, Usually, iron is kept to the inside because iron has no consequences on um, food. Even a small penetration of iron into food wouldn't create problems. This is not the case with tin, which was instead usually used on the outside. As the consequence, these two metals, in some cases, tend to be detached from each other. Also because there is a chemical effect, also because uh, different metals have different abilities to be oxidized. There are some metals which are easily oxidized than others. We say that by saying they may have different potential, different electrical potential. And of course, you can measure that into corrosion studies, as I'm showing later on in this lecture. We can, of course, decide to measure the potential to show which metal is proner to corrosion than the other. It's more, in a sense, it's more anodic than the other. If there were these two metals to constitute the two electrodes, the more prone to oxidation would go to the anode, and the other one would constitute the cathode. This causes a propagation of corrosion into the case of tin cans, like wires, so a filiform corrosion, or more extended area like lamellae. So in the longer run, they tend to detach from each other, and this is again corrosion. Then you have hydrogen embrittlement, because in the long run, the exposition to hydrogen, which might come also from the long time exposition to acids, because of course hydrogen ions are released by acids. This is a phenomenon which is not completely clear, I would say, whilst the other are, all the previous examples I was doing, they are pretty clear in engineering terms. In hydrogen embrittlement, although it is well known, from a physical point of view, it's not obvious to explain. There are theories which were more or less appropriate. I will expose something later on. Anyway, it is a serious problem. You can see also the possibility of having a biological corrosion. I will talk about biological corrosion, like this one. This is the sorry if I correct this because I didn't have time. You can find out that, for example, can have a biological effect in, for example, in concrete. You may remember that concrete is formed by calcium carbonate and you have aggregates, then you have stones or small stones or sand, etc. And if this is reinforced concrete, then you have also steel bars inside. Steel bars which take the tensile action, which are subjected into tensile force. Whilst in the other case, you have the case of concrete. In the case of concrete, you have these are prevalently subjected to compression, compression loading. In fact, we typically do compression tests of concrete. And if water is too hard, which is not the mechanical hardness, it's the chemical hardness, you may remember that water are hard if they contain too much carbonates. Then, if they contain too much carbonates, because I need to move a step back. To produce cement, you need to act with water. You need to have a definite water to cement ratio. And that the water you use might be a hard water, might contain a lot of sodium carbonate or sodium hydrocarbonate, and therefore you might find the case that there are some carbonates which are dispersed into, they are not soluted into your cement, but they tend to come to the surface. If they come to the surface, you can combine a chemical and a mechanical effect, because in fact they might become more fragile, more brittle, and then they can produce some mechanical performance reduction, some decrease of mechanical performance. Also, they can give rise to a chemical attack. We'll discuss of the concrete later on in next few lectures, so I'm not going to details about that. There is another way of corroding, which is typical of steel. Steel, austenitic steel in particular, austenitic steel has got chrome and nickel. Nickel allows the austenitic steel to be more ductile than the ferritic steel. On the other side, to protect austenitic steel corrosion, we need to have some amount of chrome. It is typically 18%, and it might happen that chrome would precipitate at the border of the grains in steel, which creates chromium carbide, some chromium carbide. It will precipitate together with carbon, because of course steel would contain some carbon. It is likely that you have a steel close to the eutectoid point, so around 0.8, 0.9 carbon. So as the consequence, you have the formation of chromium carbide, which have the effect of making further corrosion between. I remember you that corrosion can be avoided through the formation of passive layers, oxide layers. So passivation means that you form some oxide layers which are stable. Stable mostly because they are chemically stable, in the sense that they don't allow oxide to penetrate into corrosion to, they don't allow to be corroded since they are also very thick, quite thick. When I say quite thick, I mean 100, 200 microns, which might be sufficient to provide the defense against corrosion. Oxidation and corrosion are not synonyms because in the end you have an oxide, so it's oxidized, a passivated metal like titanium or aluminum, but there is no corrosion in the sense that there is no matter flying away, being brought away, and the material doesn't lose mechanical performance. With iron, you don't find that easy, and in all cases, to create some thick oxide layers. And so what you do in reality, you cover steel with other metal, which is not usually we use zinc, and what is done, you create that galvanization, and in practice, you immerse your steel into a pot of molten zinc, and normally you perform then a hardening and tempering process. So you create a layer, protective layer, which is not an oxide. It's a real protective layer, and therefore you are able to avoid corrosion once again. So this is a scheme. In practice, you need always a heat treatment furnace because you need that heat treatment. Also after the process, because you heat it up steel, but in the end you need also to temper it again to cool down in a controlled way, the slow quenching. You need to cool down in a controlled way to avoid stress accumulating. Um, and therefore destroying the galvanization. Filiform corrosion, as I was saying, these are the examples of corrosion. You have the thin layer of a can. Of course, another possibility is that you have filiform corrosion with paint or lacquer, because you may have some conductive paint. So paint with particles or with powders obtained from metal, like zinc again, or other metals. You might also have chromium, vanadium, heavy metals in many cases. And in that case, you may have the detachment of that paint. This was also typical of some car paint. Now car paint tends to be more plastic based, like acrylic based. But in some regions of your car paint, which is treated with metals again, although it's mostly acrylic, etc., you might find possibly some you have this metallized paint, which in the end tend to be detached also at interstices or at parts where you are not able to access even for cleaning, etc. Magnesium alloys are, magnesium is interesting because it is the structural metal which has the lowest density. It hasn't been applied that much in reality because it is applied in alloying, for example, with aluminium, and as such, magnesium alloys haven't been much applied. Apart from some application into the automotive sector, it is very light, but on the other side, well, it's ductile, but it suffers a deformations which might be not very controllable in some cases. What happens is that you can have in magnesium a number of different options of corrosion. Since it is very light and you might have also the possibility to compete also with some other light but not structural metal, which is calcium, and for forming salts and so on, forming filiform corrosion again. It suffers hydrogen blistering and tends to as well by forming blistering, well, locally forming blisters, which is called as the wedge effect. Forms structures of blisters, which might affect the resistance of the metal itself. And you can have some galvanic corrosion due to the presence of anodic and cathodic parts regions into the metal, therefore to form dipole. And the formation of the dipole means that some current passes. This is important to remember. If there are local anodic and cathodic parts, then this part of the metal behaves as a dipole. If there is a dipole, that means that some electrical current can pass through the metal, provided that a potential is applied. So if I apply a potential, then some current passes. Magnesium has some problems in controlling its deformation, especially because it has difficulties to be heat treated, therefore is not usually used. But its relative stiffness and relative strength are very high because its weight, its density is low. When I talk about relative strength or relative stiffness, I mean stiffness or strength divided by the density. Since the density is 1.8, gets to the level of carbon fibers to be here, to be able to compare, it weighs less than glass fibers. Therefore, its relative strength of stiffness is considerably high. And about hydrogen embrittlement, what causes the fact that hydrogen penetration into the metal would create that kind of embrittlement? So it becomes brittle and it might break. Also, in quite sudden way, it might create a corrosion which causes a decrease of strength and stiffness, and then breakage. What happens is that hydrogen embrittlement is connected to the previous presence of some cracks. When we say cracks in metal, we say defects. There are some defects. Possibly, I can imagine that metal has been in service for quite some time and then a crack forms. Fatigue can create cracks, you know it very, very well. That, for example, in structures, coming back to the example of bicycle frame, you can see crack appearing, even a visible crack. The crack might have a tip which is sharp or blunted. If you have a sharp tip and there is no hydrogen, as time goes by, it tends to be blunted because the steel or metal has got some ability to self-repair the lattice. The lattice tends to rearrange in order to blunt the crack. If hydrogen is there, there comes a very acid environment, so a kind of pit, which results in also blistering. In the end, you see that after this, the tip of this crack, you might find that there is another area which is gradually penetrated and opened. So the crack becomes longer, and in the end you end up with cleavage. Cleavage is a kind of shear fracture, which is typical in minerals. For example, the cleavage, which means the breakage with parallel layers break. One separate one from the other, and then the piece comes to. So these are some types of corrosion. Then there is also biological corrosion, as I was showing in the example of concrete. You can have also biological corrosion in metals, especially when we immerse metal. Consider a pipeline which is at sea, and the pipeline is subjected then to salted water. It's subjected to a pH which might not be neutral. You might have an acid or a alkaline. And there is an action from some bacteria. There is one important thing to say. There is no material which is totally non-biodegradable. Also, steel suffers some attack from bacteria. What happens is that it forms some kind of slime due to the presence of algae, because we are at sea, presence of algae and presence of bacteria. Possibly the surface might be rough. That's why they try to paint, although the painting doesn't resist much at sea. But in some cases they try to protect it, not for the surface not to be very rough. If the surface is very rough, or if you have again polarization, the formation of the dipole, some parts are more anodic and other ones are more cathodic, so there is a possible passage of a current. Then the slime forms, the kind of slime which includes the secretes from bacteria, algae, and in the end you have this kind of microbiological influence corrosion. That means there is no just biological corrosion, but there is also biological corrosion. There is, because corrosion can be of three types, we can conclude. There can be a chemical corrosion, so the fact that there is a dipole. Mechanical corrosion, so the fact that the material, due to the fact that the material has been used for quite some time, so there is an effect of stress going up to the limit level, close to the material strength, because possibly there has been a reduction in thickness due to wear and so on. Fatigue. The material has done a number of cycles. You may also consider that even water passing into a pipeline, or water or oil passing into a pipeline, means that there is a cycle. There can be considered cycles, because they produce some deformation or some small deformation, but even important deformation of the pipe. And I mean, it's important over time. Not important, might be a small deformation, but it's important over time, in the fullness of time. Then there is the effect of biological organisms, microorganisms. So these three types of corrosion: chemical, mechanical, and biological. Of course, there is, as always, there is the effect of the pH. There is the effect of previous pitting. Because, for example, there is some concentration of acid in some part of the pipeline, if we stick to this example, and the pits can help bacteria to progress further. And you end up with corrosion. Corrosion means the asphaltation of some part of the structure, the loss in mass and thickness, of course. So, if we were talking about fatigue. Fatigue is cyclic loading. Let's go a bit further into fatigue because we are going to talk about fatigue in a number of materials. Fatigue is a general concept. Fatigue is cyclic loading. Cyclic loading means that the material is subjected to a loading which goes from a maximum to a minimum and which might be just in one sense. You might have tensile cyclic loading, so which goes from 0 to a tensile stress and then come back to 0. Or we can have tensile compressive, for example. This is a symmetric one. This example is a symmetric one. So you go from 0 to a tensile stress, then you go to the same compressive stress on the other side, then you repeat that cycle for a large number of cycles. I would like to point out that the idea of fatigue loading is to try to predict the life of a component. Is to try to predict the life of a component. Therefore, we don't do a few cycles. We do a considerable number of cycles. Coming back to your example with your bicycle chain or your bicycle wheel, for example, you may consider that the race of your bicycle wheel can be subjected to tensile and compressive stresses due to the impact on the road surface for millions of times. And therefore, when we do fatigue loading, we therefore millions of cycles at a stress which is not a very high stress, but it's not the stress, the ultimate stress, but it's lower than the ultimate stress. Fatigue loading needs to be performed between the stresses which are likely to be the normal use stresses. It's obvious that you don't load your bicycle wheel at ultimate stress because otherwise it would break. And this is obvious. So we measure which is the ultimate stress in the idea that we want to use the bicycle wheel at a stress much lower than the maximum one. And so everything seemed okay end of 19th century. Then people discovered there has been a number of studies, for example, by Griffith, by Waller, by Bible, on the effect that even if there is little load, the structure might break suddenly just because of fatigue, because of even if there was no evident wear, so the material was not consumed heavily, it would be break anyway for fatigue. Let's apply that to a wing of an aircraft. and you understand the problem. That's why they started studying a lot fatigue. So we have a load ratio. In this case, it's -1. It's -1 because we have symmetrical cycles. So is the ratio between the minimum stress and the maximum stress of the fatigue cycle, which don't mean, of course, the ultimate stress. The fatigue cycle is much narrower than the maximum stress, the ultimate stress. We found out that this is performed quite rapidly because we want to predict the life, and of course we don't want to wait for 10 years to understand that our aircraft wing will break in 10 years. We want, for example, to reproduce it. We want it to last 10 years, for example, and then we perform fatigue loading in a much shorter time. We may do, for example, 10 cycles a second, so that in 5 days we would have reproduced the behavior of 50 years, to say. Of course, it depends on the structure, but the idea is that acceleration of aging. See in a few days what would happen over decades. Then we have fatigue failure, which is recognizable as from the presence of rings, on the structure. You see of the price. And of course, fatigue allows crack propagation, a sudden crack propagation. It's not a kind of gradual blistering as we were seeing before with hydrogen embrittlement. This effect of fatigue might be that that crack, for example, that you see can progress and creating a surface even in different directions. As you can see, you have a small crack which suddenly progresses in both senses to create failure. So that's why it is important to study fatigue. Steel has been, as always, the first material to be studied in a scientific way. So this is the material which material science was generated, the scientific study of material. Steel has got an advantage in terms of fatigue, and this has been recognized in some curves. These were studies which were started by Bowler, which has done these studies about the SN curves. The SN curves, with N we have the number of cycles. With S we have the amplitude of the fatigue cycle. SA is amplitude of the fatigue cycle. Then what do we have here in practice? On the y-axis, we have fatigue cycles of different amplitudes. You may remember the previous slide. In the previous slide, you can see this amplitude. You may start with the maximum amplitude you are interested in, which is the use stresses, which relates to the use stresses. So I have the maximum tensile stress during use and the maximum compressive stress during use. Of course, symmetric, they might be symmetric. In many cases, they are not symmetric. In many cases, for example, steel doesn't go into compression. But let's assume for simplicity that it is Einstein. So you have R equal to -1. Um, you load with this maximum. There are three phases in your life. Cycles simulate component life. Three phases on this life. For some, this is a logarithmic curve. Until a certain point, in the case of this curve, this is a represented curve. Please don't stick to the number. It's more important. The ideas are more important. That there are three phases. In one phase, in the first phase, when the material structure is new, you are able to withstand these. You are able to withstand this amplitude of fatigue cycle without undergoing fracture, fatigue failure. Then, in a second time, you have some kind of wear, some kind of degradation of properties, and therefore you pass to a high cycle. You pass to a high cycle fatigue in the sense that the cycles are becoming higher. You have making the material work for more and more time, and therefore the material is no longer able to withstand the maximum amplitude cycle, and therefore the cycle needs to be reduced if you want to keep the material safe. There is a certain point at which the amplitude is reduced. In the third phase, if you have a very high cycle number, for very high n, you find out that there is a fatigue limit. This is true only for steel. That at a certain point, you may carry on doing fatigue tests to the infinite. Of course, at that low dimension of the fatigue cycle, so you have reduced the amplitude of the cycle. You have reduced the amplitude of the cycle to a point at which you can carry on to the infinite. Of course, this is theoretical, but it's on the other side, this is also promising for you to steel, because you may consider that there is some kind of loading below which you would not undergo fatigue failure. You would undergo other types of fatigue because then there is wear, corrosion, etc. But you would not undergo fatigue failure under a certain amplitude of the fatigue cycle. This is meant as this is referred to as fatigue limit. This happens for steel. This doesn't happen for aluminum, for example. Aluminum doesn't have any fatigue, any clear fatigue limit. If it is too old, it might undergo fatigue fracture, even if the load is very, very, very low. Even if the load is close to zero, it might undergo fatigue failure. In practical term, this says to you one thing, that other materials, glass is even worse. The material might break. Plastic, some types of plastic is even worse. That even if the material is not loaded, it might undergo fatigue. At a certain point, it will break without any load applied. This doesn't happen with steel. That's why we stick to steel, although there are other materials. because other materials have no fatigue limits. And therefore, they might break for fatigue even if they are not. Then there are some other elements to be suggested in practice and to be dealt with. In practical terms, I am showing here some two tensile compressive fatigue samples. They are not very different from tensile samples. They are shorter and thicker in a sense. They tend to be cylindrical with always a reduction of thickness in the grip length in the part which is from which the grip length is the part of the sample from which the measurements are taken. So the central part. The other part, the extreme parts, are just to be taken into the grips to be pulled or pushed. Okay. Then there is the influence of notches. Because there is a fatigue limit, there is one important thing which I didn't say yet. That steel has a fatigue limit if it has no notches, no cracks. A notch is a crack which has been done to promote failure and to do tests. If there is no cracks, we can be sure of fatigue. Otherwise there are problems also for steel. Anyway, it remains the best material for doing a long use at considerable load. Corrosion. Let's come back to how we measure corrosion. We were saying how we measure in particular electrochemical corrosion, which is the most common one. The most common one, also because it's diffusing practically all conductive materials, therefore in metals, and wherever metal is present. Also like in reinforced concrete, for example. And as I was saying, electrochemical corrosion can be recognized by the fact that some electrical current, expressed, as you know, in ampere, passes through a circuitry which we can induce the passage of that current by applying a potential. We apply a potential, and we see which level of current passes. We can measure that, but we need a reference, of course. And the reference, our reference, is a reference electrode, which used to be, but is still used for corrosion measurement, is still used in scales to compare different materials. Although now a slightly different electrode is used. And it was the calomel electrode. Calomel is mercury chloride. And mercury chloride now has been replaced by silver chloride because of the fact that silver is harmless in comparison to mercury. And also for the accumulation of mercury into the environment. But apart from these considerations, as a reference, the SC standard calomel electrode is still the reference to measure all the performance of the other material with respect to it. In a solution of potassium chloride and a saturated solution of calomel, because otherwise something would be missing into our reference. So we need also to establish which is the concentration of the solution. What we end up with is that we have a polarization curve. So we apply a potential, y-axis, and we get a current density from which we can transform into a corrosion rate in practice, or in a corrosion velocity, if you wish. A corrosion velocity is given by the intensity of current, considering the equivalent mass of the metal, etc., and the constant. But apart from this consideration, what is important is that in our application of a potential, we distinguish three different regions. Of course, one would need to have an electrochemical corrosion in the process, otherwise no current would pass. If current passes, it increases, sort of increases, because it's not, as you can see, the proportionality is not always the same, but in general terms, it increases with the potential we apply. There is a first potential. With low potential, there is a kind of direct proportionality with the current. It's a kind of ohmic, according to the first law, Ohm's law behavior. There is no corrosion up to a point where you get a critical density of current, a critical current density, a high crit. And for a definite potential, which you know better, of course, because you have a potential stat, and so you are measuring on the potential stat, and therefore what you see is the potential from which you see the current density. And so you have no corrosion up to I crit. Then you have corrosion, which means passivation, which means that your material becomes passive, so might be prone to oxidation, definitely prone to oxidation. So a lot of the current is consumed to have this oxidation in the first place. Then you have a steady growth of potential with no current growth. In practice, you have this phase of passivation, which means oxidation, but doesn't necessarily mean corrosion. It would mean corrosion in the case your oxide is not thick enough. If the oxide is protective, you don't have oxidation, you have passivation. Then at a certain point, you resume the ohmic behavior for a transpassive situation, where in practice the sample is fragmented, and you get even to a mechanical failure because you have an uncontrolled passage of current in corrosion situation. So it leads in the transpassive area, leads to the failure of your material corrosion. Oxidation and also corrosion, because also the passive film, passivation film is broken together with the material. So of course, these curves, we have one curve for every material and every pH. or to say it better, for every material, we have a number of these polarization curves for every pH. I'm showing just to conclude an example of this situation. For example, this is the curve in reinforced concrete at pH between 13, over 13, between 13 and 13.8. And it's basically about the same curve. And you basically have an immune zone with a very limited passage of the current, which I don't show, and where hydrogen can be developed, which is immune from corrosion. Absolutely immune from corrosion because it's an active zone. Then you have this interval. It is very interesting because this doesn't happen for other pH, for the reinforced concrete at other pH. But at a very alkaline pH, what you have is thermodynamical stable oxides and hydroxides of iron inside. Please remember, iron is inside the concrete. You have iron bars inside the concrete. The environment is very alkaline and it's really very protected. Then in transpassivity zone, of course, everything is destroyed. But if it is, if you stick to having this kind of potentials, and you may play on it, by selecting the right iron and to try to have the right amount of salinity into your water. Please remember that we are with concrete, and with concrete, the type of water with which we produce concrete very makes a lot of difference. For example, the salinity of the hardness, the salt content in general terms of water, salts of the calcium, potassium, magnesium, and so on, would change, and the presence of salt, of course, would change a lot the behavior. But we can be sure that if we stick to these potentials with respect to the SCE, the standard calomel electrode, we might be sure that we have no corrosion. And this is important because if steel bars are corroded inside the concrete, since it is a composite, we lose the adhesion between the internal bar and the concrete, and the concrete would eventually fragment because it is no longer adherent to the technological. To complete my lecture for today, I present you with the galvanic series in the particular case of flowing seawater at ambient temperature at sea. And you can see a few things which are important. So let's look at the zero. There are just a few materials which are left of the zero, so which are active with respect of the calomel, active, so they act as cathodes with respect to the calomel electrode, and these are gold and platinum, which you may easily know they don't suffer any oxidation, and graphite. In fact, we do electrodes with graphite exactly because they don't suffer oxidation. All the other materials are to the right side of the calomel electrode, of the standard calomel electrode. Please also note that you have some white rectangles which represent instead the conditions in acidic water instead that of seawater. There is a quite considerable difference. And you may easily consider that the higher you go and so the lower value of your potential, the more oxidized, the more passive get your material. In practical terms, even stainless steel, and unless it is in acid condition, and nickel chrome alloy as well, unless they go into stainless steel has a different behavior when it is in acidic water instead of seawater. These are not very good conditions because, for example, copper behaves much better if it is not in salted water, and tin as well. But this serves for you as a reference. Aluminium is one of the first ones, and zinc is one of the first ones. Titanium is not there, but it's quite close. It's not there because it's not needed at sea for other reasons, but it's also too expensive to be used at sea. But you can see that aluminium gets easily oxidized because it's really very passive, but it gets very thick layers of oxide, so it's passivated, and you can anodize it. Since it serves so well as being an anode or anything else, you can couple it with any other metal, really, apart from zinc, and you can increase even the thickness of the oxide layers. So you anodize aluminum, as we were saying last time. Magnesium is the more unfortunate one because in reality, well, the oxide layers are not as good as the aluminum ones, and it tends to be anodic in comparison to any. Okay, we can progress later on next time. Next lecture on Monday, where we try to complete that evaluation about metals, and of course we will come to them also later on, because of course material science starts from metals, developing them for other materials. You can see that also with corrosion you may find a number of possible research teams, it's an exhaustible research team, corrosion in a sense. We try to move away gradually from the ideal material, because for corrosion, for fatigue, for tensile tests, we have seen that steel is the closest to the ideal material, so the homogeneous, elastic, and isotope. Then on Monday it will be the last lecture before Easter. Then we're going to resume on the following Friday. So we have one more lecture before Easter. Then we will resume on Friday the 17th. So see you on Monday at 4, and have a nice weekend.
Grazie, arrivederci.
Arrivederci, grazie.
Arrivederci.